Yes, can everyone hear me? Hello?
Yes, sir. I rate you 5 out of 5.
Okay, fantastic. So like I said, right, where are we here? Okay. So you've got a gas. Initially it was 0.25 meters cubed. And then we apply some heat into it. Heat at CP. And then what tends to happen is that in this case, the gas expands, right? So we got a bigger volume of gas somehow. I could have drawn this a bit better. And of course, your parameters like your initial temperature, this was initially 15 degrees, and a pressure, it's at constant pressure, so the pressure doesn't change for both at 1.5 bar. And what we're looking at is what happened to the temperature, of course, and of course the pressure remains constant because it's being heated at constant pressure. Okay, I have a question. What do you think is going to happen to the temperature? I'll just create a poll here. I'll just start do something quickly. Just quickly see. Will the temperature increase? Okay, what will happen to the temperature? Sorry, let me just get that right. What will happen to the temperature? Okay, increase or decrease? What happened to the final? Or what happened to the temperature at state 2? Look at rather. What happened to temperature at state 2? Okay, cool. I'm having a poll here. Let's see. So what do you think is going to happen at the second state? Will it increase? Will it decrease? Remember, the gas is expanding. You could think of it as an aerosol can. You bind the odorant sprays, gas is pressure, it's compressed to a specific volume, maybe expand. That's one way of looking at it. And remember Charles' law, Boyle's law, an increase in volume. What does that mean? So we'll see now. So it's looking interesting, it's looking even. Okay. Can everyone see the poll? Hello?
It was there, sir, then it went away again. You can see the poll, the options.
That's back. So can you see the increase, decrease? Okay, so most people said an increase. Well, not most, yeah, well, in comparison. And let's say the decrease. Let's solve it and then try to figure out exactly what is going on. So more saying decrease. I'd like to hear your reasons why. So I'll stop the poll now. It's okay. It's still more on the increase side, yeah. Okay, fantastic. Increase all. That's fine. We can stop the poll. We can continue with the actual solution. Okay, so part A of the question, they've asked us to work out the mass of the gas, right? So I'll just say A. Who can tell me how are we going to compute this? Who has any idea? Which formula are you familiar with? Anyone? Is it rust or should I proceed? Wando and Keaton, I can see you guys are you guys?
Yeah, it's PV equals MRT.
Fantastic. So PV equals MRT. Guys, this is a very important formula. Take note of this one. You'll be using it a lot in your gas powered cycles. Okay, so we're looking for the mass, right? So you can use state 1 because we have, so that's P1, V1, R1, T1. It's worth to note, because it's a closed system, right, that the mass remains constant. For both states, because it's a closed system, right? An open system would be, for instance, air flowing through a window would be one, whereas a closed system would be, like I said, in a piston chamber. But anyway, nevertheless, let's proceed. So it's 1.5 bar, which will be 1.5 times 100 kPa times the volume. In this case, our initial volume was 0.25. Mass is unknown of the system. They give us a gas constant of 300 kilojoules per kilogram Kelvin. In this case, it's just 300. And then they give us the temperature, right, which is 15 degrees. But we have to convert this into Kelvin. Okay, so now we can solve for the mass. So let's quickly see what we get. I just want to open my calculator quickly. Where is this now? Okay, give me a second. Where is my calculator? Okay, can everyone see the calculator? Hello?
Yes, sir.
Oh, fantastic. It's 1.5 times. Can someone talk me through this here? Times 0.25? That's correct. Hello? Are you guys working through this?
Correct, sir. That's correct, sir.
Okay.
Divided by 10 times 15 plus 273.
Okay, 15 plus 273, which is what? Okay, let's just type it in for everyone to see. 15 plus 273 multiplied by
300.
300. Is everyone in agreement with this? Okay, let's click equal. Is that the answer? 0.434 kilograms. Yeah, I'm not sure what that is over there, but 0.434 kilograms. That's what we get. Okay, so I'll just close that guy off. I'll just share the I'm so 0.434 kilograms. Okay, is everyone happy with that? Hello?
Yes, sir. Fine with it.
Okay, fantastic. Right, so let's proceed on to the next one. So what they require now is the final temperature, right? Okay. So again, we use our equation of state, P1, V1, or T1. That's before and after, exactly the same. But in this case, our pressures are constant, so we can eliminate those, and then we can basically find our temperature afterwards. So now we can actually see what's going to happen to the temperature, even though we have that answer there. So that's going to be 0.25 over, that should be 288 Kelvin. That's just 15 plus 273 equals the second volume, and that's going to be 0.75. And you're looking for T2. Right, okay, so T2 then will be 0.25 over 288. And you could say it's times 1 over 0.75. What do we get? What do we get?
864.
864. 8, sorry. 864 Kelvin. Is everyone happy with that? So, if you said it increased, fantastic. Tell me why. Who can tell me why, please? Anyone?
It's because of Charles' law. So
Charles' law, right? And what does Charles' law state? It is an increase in volume.
yeah, the volume is directly proportional to the change in absolute.
Yeah, fantastic, fantastic. And one could also look at it from a perspective of that heat was being added to the system, and then heat essentially increased the temperature. You can actually do this with to test this out would be taking a syringe with some air in and then actually heating up the air, heating up the syringe with the air within the syringe, and you could actually see the piston move. So that's an interesting experiment to do regarding this. Okay, so what I'll do now, I'll just clear up this quickly. Just erase all of this and then do the next one. Okay, cool. So just remove that. Okay, so we had C now. And C requires us to compute the work done for this process, right? So looking back at our non-steady flow equation, what we can do now is find the internal energy, which will be mass times CV times T2 minus T1, and find our work done, right? So our work done in this case would be pressure times V2 minus V1. The addition of those would give us, oh, sorry, we're looking for the work done, sorry. So this is what we're focusing on for now. We'll be getting to that. So the work done in this case once again, you can just picture the work done here. In this case, would be like a piston arrangement over here. You can sketch it up, and as it's being heated, as heat's being applied over here, the piston essentially moves back. So from that state, or in this case, it actually moves forward due to the. Okay, let me just erase all of this. Sorry, there we go. Okay, so we can just delete all of these quickly. So the pressure in this case was 1.5 times 100 kilopascals, and our change in volume was from 0.75 to 0.25. Something very important about this. So what do we get over here? What is the answer for this one?
75 kilojoules.
75 kilojoules, right? But what's important for you is to indicate what's happening. So because we're dealing with positive work, so the work is greater than 0, this is considered an expansion process. Is that correct? And what it also means is that it's work done by gas. This is very important. If you are considering how it mark, you'd get a mark here. I'll show you now. Maybe a mark here. Okay, that's a bit thick. Something more red pen like. Should get a mark over here. You get a mark over here, and you get a mark over here. So it's very important to understand what is happening with these equations and the senses. What does positive and negative mean? It essentially tells that you understand the process. Okay, so that's that there. So what we can do now, we can work out D. And D is the change in internal energy, right? So I mentioned to you, and this is something I want to discuss. That's MCV T2 minus T1. The mass was 0.434 times our CV values given to us over here, which is 73 kilojoules or 730 kilojoules per kilogram, and then our temperatures here, this is T1. T1 is 15, and okay, we can just use the Kelvin. So it's 864 minus 288, and we should get a value. What do we get over there? What's the answer to this? It also looks like an increase in energy anyway. What you guys get for this?
182.5 kilojoules.
Okay, let's have a look. 182, you say?
182.5.
Oh, okay, sweet, that's fine. So, again, the mark allocation in this case would be the substitution, the answer, and that. What's important to note with all these things is you can basically see how they're all interacting each other. And what I'm talking about is the pressure, volume, temperature, internal energy, work, and heat. So what happened here? We supplied heat to some gas. It expanded due to Charles' law, right? And then, and as it expands, we have a sense what happens when it expands. We get work being done by the gas, and likewise on the other side, we get an increase in internal energy of the gas. So the gas is able to, essentially what it really means, it has more energy to do work. We give in energy. Because I mean, the internal energy is made up of a lot of counterparts, like the kinetic energy of the particles, the potential energy, the vibrational energy. There's a whole note on internal energy, which we should probably go through at some stage. Okay, and then at D, oh, you have D now, so at E, so I have E on top of here, just erase this. Let's get my erase over here.
Sorry, sir.
Yes, fantastic.
I don't know if it's from your side, but someone sent a message in the group saying the chat is inactive, meaning they can't send messages in the chat.
Oh, I wonder. I see that's a problem. Oh, okay, I see. It should be sorted now. Try now.
Yeah, I see it's working now, sir, because some people commented in the.
Oh, I see. You guys can raise your hand and ask questions, eh? These are allowed. So we're currently at E now, right? And to find the work, or sorry, the heat transfer, it's simply the sum of the internal energy and the work. So in this case, it's going to be 75, or well, not 75, it was 860. Just what's going on here? 182. So 1.5 plus 75. Of course, they're both in joules, so that's okay. I just want to fix this up quickly. Okay, I'll check the chat now. Aku posed a very good question. I'll explain to you what's happening regarding that. So if we add those two guys up, what do we get? Do we get 258 something? 256?
257.5.
257.5. Fantastic. Now, what I just did was a long way in order to compute this, right? The other alternative is to actually, I'll just erase this. This is what you mean, Yaku. So what we can do now is find the heat using the shortcut, and this would be the mass times Cp times T2 minus T1. This is how you can do that now. So let me just erase this as well.
But in this example, they don't give the Cp value.
Yes, but you'll get to that. No worries. So you guys do remember that your gas constant is equal to Cp minus Cv. There's a relationship for ideal gases, right? Once again, this is division, so it's fine. We can always unpack this if need be. So gas constant in this case I think was 300 plus CV was 730, and here we should get 1030 joules per kilogram Kelvin. That's how we can find the heat basically. So there's two basic ways. It's essentially the same thing. But that's why you have to be very careful. Like I mentioned, when you're using internal energy, always use your CV value, right? And we can discuss why. This can also be written as M times change in enthalpy. And this is also important, but we'll get to this. So our mass was 0.434. Our CP value is 1030. T2 was 864 minus 288. The answer should be 257.5, which should be close to the previous one. Did we get that? Mr. Vasson, Mr. Akawa, is everyone happy? Ms. Duba, get the same answer? Yes. Okay, so that's fantastic. Okay, so these are very important, and you'll see why when you start going. So, can I move on to the next question, or is people still absorbing this? Is there any questions regarding this one? Can we move on? Yaku says fine. Just wait. I need a seconder.
Yes, you can move on, sir.
Okay, thank you. Okay, so I'll be going back to my slides quickly. Just gonna stop sharing that. So we've basically done. Just taking some time to share first. Yep. So what we've basically done is, if you look at the table, you've done the constant pressure one, which is the first row, and you've done the constant volume, which is the second row. I just want to zoom this quickly for you to show you. Let's just move this down. So Yaku, I don't know if you can see this over here. That's your heat added over there for the constant pressure, so it'll be CP, whereas the constant volume is CV. So always remember that CV is for internal energy. So this basically this is a summary of all the relationships between pressure, volume, and so forth. So that's just worth noting over there. That's basically that. Okay. Now I want to now I'm going to skip over to, so question number 3 is isothermal. And it's a very short one, but isothermal essentially means over here that T equals 0. So if you look at your PVT over PVT, state 1 and state 2, essentially that and that falls away, and you can basically compute that around this. What's also important with this, so I'm going to move on to something else, is that your internal energy, this is very important, equals 0 because there's no change in temperature. No change in temp. Which also tells you, according to Joule's law, if you've seen it, that internal energy is solely a function of temperature. Well, that's not entirely true, but that's the idea here. So you guys can do this on your own. It will be given to you. So that's not a big deal. It's quick to do. What I like to do is actually going on to the polytropic one. And the reason why I want to go on the polytropic one is this is the actual, these are the laws we're actually using to model internal combustion engines. So I want us to give a go at this one over here, and let's see how it goes. So Mr. David, the first question is, so basically we have some air, right? I'll sketch it over here. Then air has a volume, it has a pressure of 10 bar, and it has a temperature of 50 degrees. It expands, right? So the volume once again increases. Okay, so it becomes 6 meter cube. This could be the power stroke within the, or the expansion stroke within the ICE. And of course, we're looking for now P2, I think, and we're looking for not a V2 and T2. Okay. So again, can someone besides Kieran, who's mentioned to me earlier on, how do we solve the mass of air? Leletu, Anati, Puleng maybe. Fantastic. PV equals MRT. Jaco doesn't play around here. So for A, it's PV equals MRT again. So pressure at point 1 was 10 bar times at 100 kilopascals. Our volume was, in this case, 1. Looking for the mass, and our gas constant at this temperature is 287, and it's going to be 150 plus 273. Okay, what do we get here? Do we get the 8 kilograms? 8.25? Let's see. Did everyone get it? Mr. Barao, I'm skipping that example. Let me return to it afterwards. Don't worry, I'll return to it. I just want to get to the necessary stuff here. This is where you'll be at. I'll return to it after this question. There'll be no problem. So I hope everyone got the mass over there. Should I show my calculator again? I don't think it's necessary.
824.
824. That is fine. Thank you. So it's 8,24 kilograms. Fantastic. That's a lot of mass for air. So now we talk about the final pressure, right? So what you must know of this is that this is not like the other laws. where you just go PV, or we can do PVT. However, in this case, there's an index, expansion index to the power n over here. So I can show you back over here to these formulas. If you have a look at this one, I'll just have to choose this again. I can delete this and delete that for now. Is that you can see over here, those are the laws you're going to be using for polytropic processes. What's important for you to understand, and I probably didn't explain it well, definitely, is that polytropic means many processes in one. You could basically look at it as the most accurate model to look at ideal gases and the interactions. So it includes constant, where all of these things are acting at the same time. So that's why I think polytropic was very important. Combination of all processes. So important, right? Just delete that. Okay, so let's proceed here. So first pressure was again it was 10 times 100. The first volume was 1, so that's times 1 to the power 1.2, and we find the second pressure, and looking at the volume of the second one, it will be 6 to the power 1.2. Because the volume is increasing, you're expecting a decrease in pressure. So I'm pretty sure that is happening over here because the volume is increasing. So what do we get for P2? So we're basically going from, let's see, from 10 bar, what do we get?
1.165 bar.
Fantastic. So that's if you have a look at that, 1.165 bar. Of course, probably divided by 100 kilopascals. So we went from 10 bar, right, to 1.16 bar. This feels very realistic. I mean, the pressure was initially 10 at 1 meters cube. We expanded all the way to 6 meters cube, which is fairly massive. So of course our pressure should drop. It's nearly atmospheric pressure over here. Nearly. Okay. So now that's fine. Now we can do C over here. Oh, I have to clear this up eventually. So C, you have to be using now, again, going back over here. We can use either this guy over here or that one over here. So we can basically use T2 over T1 equals your two volumes, V1 divided by V2 to n minus 1. What normally happens is students normally confuse it, like this, the V1, the initial state and the final state. So always be careful when you're using these formulas. So it's T2 over T1 equals V1 over V2 to the power n minus 1. So just quickly solve that. That's T2 over T1 equals V1 over V2 to the power n minus 1. Okay, so what I'm expecting is for the temperature to, so the pressure has dropped. So according to Monton's law, our temperature should also decrease. So this was initially a very hot chamber, and we expanded. So I'm expecting a nice increase, a decrease in temperature. So T1 was 150 plus 273, and then V1 was 1 over 6, V2 was 6, and then this should be 1.2 minus 1. Okay, and this should be equal to something. I'll remove all of this now to make it a bit more neater. Okay, what do we get for this? Do we get the 295?
Yes, sir.
Yes. Thank you, Luando. If we subtract that by 273, what do we get? It's 295 point, what was it again? 22.6. Yeah. Fantastic. 295.6. Sorry. 295.6. So that's 22.6 degrees. Can you clear up here? So you can see from 150 degrees Celsius, a drastic drop. A drastic drop. So this is why these questions are very important. So let me just clear up here. And then we can continue with the rest. Oops. One. Just get my razor. Is everyone on the same page here? Are we all good? Is the rust coming a bit off? Okay, just lags a bit with using PowerPoint. Okay, that should be adequate. Okay, thank you guys. So let's work the work done right now. Let's get back here. So the work done will be in this case. So remember again our non-steady flow equation, which I write over here. So that's Q equals change in internal energy plus work. For polytropic process, we have to compute both these values. So I'm just making you aware, nothing is cancelled here. Like for instance, constant volume, there's no work done. Constant temperature isothermal, there's no internal energy. So in this case, our work will be P1 V1 minus P2 V2 minus N minus 1. Just again, this all forms part of these formulas over here, right? And what we're looking for here is whether the gas is being compressed or expanding. So in this case, our gas is expanding, so you will expect a positive work. So let's see if that is the case. You've got 10 bar again, multiply by V1 minus P2. What's P2 again? Sorry, it's 1.162. I'll just use the answers in the meantime. Of course, times the volume. Volume in this case was 6. And our initial expansion was 1.2 minus 1. What do we get, guys? You had 155 kilojoules. Thank you, Ms. Tuva. (1,505 kilojoules). And of course, it's positive. Work is done by the gas. Okay. Next, we can work out the internal energy. So again, always remember, polytropic process involves all the processes, so nothing is cancelled. So internal energy, we're always using CV. And it's definitely a function of temperature, as you can see. This would be 8.25 times 718, and the change in temperature. So that's going to be 295 minus T1, which was, what's 150 plus 273 again? Just get that right. .423. No, sorry. Sorry, that's 423. Forgive me for that. Minus 295. It's very important to put the temperatures in the correct places, so you can actually, so we're able to see whether there's an increase in internal energy or decrease. And of course, this case is an increase in internal energy. Makes sense again. The gas is expanding, so you've got more energy to use, more energy to play with. So computers, wait, I'm wrong here, eh? It's other way around again. That's what I was thinking now. What am I doing? I was too much in my head now. Give me a second. The gas expanding. My logic is being flawed now. It's my eraser just giving me problems. Just give me a second. Not sure why my eraser is going to work. Anyway, nevertheless, that should be negative, that should be positive. Sorry, what I meant to say was, oh, I can't write there. You've got a decrease. Okay, my thing is just dying out here, so I'm not sure what's happening here. Okay, I'm not sure. Yeah, so don't wrong my pen. I'll figure it out now. Yeah, so we have a decrease in internal energy, and the logic again here in this case, what I understand here is that because work is being done, and internal, it must be at the expense of something. So of course it's going to be in the expense of internal energy, hence the decrease. So this is what I meant to say, not an increase, because otherwise, if you compress the gas, it would have went up, with the temperature would have went up. So yeah, so because work is being done by the gas, there's a decrease in internal energy. Okay, so let me just clear all of this up here. Just wanna clear the PowerPoint up again. And then to find your heat, what you need to do is you need to, just gonna erase everything now. Just give me a second. Just give me a second, students. Okay, cool. Yeah, so to find the to find the heat over here, you just got to take in your internal energy plus your work. And in this case, it is minus 758 plus your work, and your work was 1505, I think. And it should end up with 742 something, 0.5, I don't know, or 741. And this will be in kilojoules, and this will be heat, it'll be heat gained. Yeah, it'll be heat gained, funny enough. It's very strange in this case here. Okay, did everyone get that? Did you guys get the heat?
Yes, sir, we got it. It's just our values are a bit different.
Yeah, no, it's fine. It was a 0.5 out the end here. There's no issues.
It's not really a 0.5. Like I got negative 753.74.
Okay, yeah, that's what I want to ask. So our work done was positive, right? Is that correct? Yes.
Yes, and then
So you subtract 758, right?
we got 753.74.
Okay, yeah. So 753.74, and then your heat will be a positive value.
Positive value of 751.26.
Okay, let me just get that. Yeah. So 751, that is fine. And I'm aware of this. 751.26, you say, right?
Yes, that's
So yeah,
correct.
yeah, okay, that's fine. As long as the principles there, it's just interesting to note, like, even though this gas is expanding, that there's a gain, there's a heat gain. So first thing is, work is being done by the gas, and then at the expense of internal energy. So basically, to do the work, there must be a decrease in internal energy, or of course the air in this case. However, overall, if you look at the values of the equation, that heat was actually gained by the system. So it's a very interesting thing to look at the interactions between the heat, work, and internal energy. Okay, so I'm basically gonna do the last one for the day. There is more to do, which I recommend you do. So let me just check Mr. Where is he now? Mr. Barrow. So once I go back to example 3, are you still sure about that?
So you're going to load this PowerPoint onto the system.
Yes. Yeah, it should be exactly after this here. Because example 3 is fairly easy, but Mr. Barrow. Okay, so you want example 3. Let's go over it anyway. Once again, so looking back at this here, right? So starting with your non-steady flow equation, you've got the change in internal energy plus work. And because no change in temp, the internal energy is 0. So basically the system is not getting any new energy. And therefore, when you're supplying heat, it's all converted into work. So this is very interesting over here. Very, very interesting. So basically you can this is the idea of insulation, right? It's that the more you insulate something, that more heat is available for work, or other way around. But normally going from heat to work in our case, because we're dealing with heat engines. So that's the idea here. So hey, they want the work done, right? So very, very easy. We go back to our table over here. You look at where the work is, and the work for an isothermal process or constant temperature will be P1 V1 log V2 over V1, right? So that's fairly easy. Oh, sorry, the heat additive. It's the same thing here. So P1 V1 log V2 over V1. So we can quickly go to this one. So work is going to be P1 V1 log V2 over V1. I think that is correct. So you've got initial pressure 1 bar, so that's 100 kilopascals times. So isothermally, by the way, constant temperature. So if you're wondering what's happening with this gas laws, all we're doing is first keeping the volume constant, then we're keeping the pressure constant, Then we keep in the temperature constant. And then eventually what we do, we integrate all of these things into one thing. PV over T. And this is essentially polytropic. So this is the gain. This is the way it's structured, or the way it's taught. Anyway, so V1 was 1, and then you can say times log, and it says a volume ratio of 8. So that's basically, I'm assuming it's going to be 8, like that. I don't know, anything else. Just check if we get the right answer. Do we get the work done? I'm not sure what log 8 is here. Check my calculator quickly. So 100 kilopascals multiply 1 times log 8. Nope. That shouldn't be the answer there. So it's probably through a volume ratio of 8. So, oh, it's compressed, right? So the volume should increase. So V2 is high. So this should be wrong here. This should be. Am I missing something here? P1, V1. Do we all get the answer?
No, sir, we don't get that answer.
Yeah,
Sir,
yes.
I get the answer, but then my answer, the answer that I get is positive. I'm assuming it's positive. I have to change the sign to negative because it's saying it's compressed there. Instead of that log, I think we're supposed to use lens. I don't know if it's going to
Oh
change
man,
anything.
that's correct, yeah. It's
Yes.
supposed to be learn, yeah. I'm looking at the bloody form sheet, yeah. That's correct, yeah. So I apologize for that, guys. I was thinking that, yeah, that's log 10 or log E. So this is learn V2 over V1. And you should get, this is going to be 8. Best, so it should be 8. Thank you, Ernest.
No problem, sir.
Let's see. Remember it's being compressed, right? So the work must be negative. So it's right.
Must be negative. Yes, sir.
Are you with me?
So,
Oh, you're saying it's positive? Someone have to say something. Yes.
yeah, I get the answer if I say ln 1 over 8, then that gives us a negative 208
Yeah, that's what I'm
kilojoules.
thinking. Yeah. So in this case, guys, this is a bit me for this one because this is a bit. I know that I skipped and I'm facing all these problems. So it's 1 over 8. Yeah, see, the issue is through a volume ratio of 8, but it was being compressed, so I'm just confused with the way it's written, but it's fine. In this case, 1 over 8, so we get minus 208. We know that this is correct because the gas is being compressed. So negative work means that it's compressed, right? And then again, B will be the change in internal energy, right? That's going to be 0 due to Joule's law because there's no change in temperature, there's no change in internal energy. That is fine. I have a better table than this. Yeah, it's log E. Sorry guys, forgive me. It's log E, so it is ln. Ln is log E. And then what happens here is that our heat transfer basically equals the work, and therefore heat is lost in this case here. So it's minus 208 kilojoules. Sorry about that one. Okay, so that's really straightforward, guys, right? Fine. So Barao. Okay, so yeah, that's basically that, right? Okay, so guys, we've done a few things. What I'd like to see now. Okay, so this is the adiabatic process. Go over this yourself. This you can do yourself. We can discuss it maybe. I don't know, maybe Monday, maybe depends. But what I'd like to see is for the next 20 minutes. You guys attempt this one. I'll give you guys 10 minutes to do this on your own, and then I will go through it. And then also once we close off, just for homework, I want you guys to do these three things. I want you guys to do, and one of them is basically a cycle question. So this is when you start integrating all the gas laws into one process, into one diagram, into one. It's one cycle. All the processes into one cycle. Sorry. So there's one you can do over here, and there's another one you can do over here. So I'm not sure when I can go over this again, but yeah, make sure that. And also, I've left a small investigation for you. Try to complete this table. I want us to discuss it. Hopefully next time we meet. And yeah, so I'd like to know what happens when the work increases, what happens to the temperature. Give me a brief explanation. So, but let's just quickly, yes, I will post that on Blackboard. I will make reminders. So this is just for homework. I will post some more notes for as or more. What's the word I'm looking for? More practice sums. But I'll give you guys 8 minutes to attempt this one over here. Let's see if you guys can solve this one. So by 12 minutes past, 30 minutes past, I'll see if you can identify which process this is and if you can solve it. If you understand your thermodynamics really well, it's a fairly real life problem. It's very accurate. Hello. Who's winning? No density, you say. That's very interesting. The gas constant of air is 287 at 20 degrees. So just figure it out. I deliberately gave this problem. That's yes. So think. PV equals MRT. Just think around that. Has anyone solved it already? Who got the mass of 57.08 kilograms? Fantastic. So guys, one more minute. Okay, can we solve it? Luando, Mango, can I go for it? Hello?
We get 90.3 degrees Celsius.
Hey, Mr. Naidu, well done, man. Well done. Should we call it a day or should I solve this?
Solve it, say.
Okay, fantastic. So, first thing, what process is this? So you've got a student living in a dorm room, right? He leaves a fan on, and the fan, all the doors and windows are tightly closed, and disregarding any heat transfer to the walls and windows, determine the temperature in the room. She comes back 8 hours later. What process is this? Can someone give me an answer before I move on? Hello?
Constant volume, sir.
Fantastic, it's a constant volume. If you did not know this, hospitality is waiting for you guys. Okay, so the first thing you can do, right? The first thing I would recommend, because of the constant volume, you look at your non-steady flow equation. In this case, there is no work being done, right? So then Q will be equal to M CV T2 minus T1. Okay, so the first thing I'll do is work out my mass, right? So you get PV equals M RT, right? So your pressure is based at atmospheric conditions of volume. You can work out 3 times 4 times 4. You're going to find the mass of air in the room. Our gas constant 287, and we have 293 over here. And when you solve this, you should get 57.08 kilograms. So that shows you there's a lot of air. 57 kilograms is a lot of air. Doesn't seem like a lot, but it's a lot. Once you have this, the next step is to look at your fan, right? So your fan is producing power. And there's a relationship between energy and power. It is essentially time. Power is a rate of energy per second. Of course, the energy in this case would be heat. Thermal energy is being generated. Yes? Got a question? Okay. So then in this case, yes. Oh, wow. So then you're going to say power times time equals Q, right? So in this case, our power is 100 watts times 8 hours times 3,600. This has to be in seconds. This will be equal to basically MCV and the changing temperature. So your mass will be 57.08. Your CV in this case is normally 718 or 7717. 78 is a reasonable value. You're looking for T2. You're finding out how much energy, how much thermal energy is going to be generated to increase the temperature, and then T1 will be basically 20. And then you can solve for T2, and you should get, let's see, you should get 70.272 plus 20, and that will give you 90.7 sorry, 27 something, 272. Is everyone happy with that? Everyone get that? Hello? Puleng, your mic is unmuted. Mr. Williams, are you happy? Chauke, Mango, speak to me. Oh, Puleng says, please explain it again. Okay, so, right, so student lives in a dormitory room, right? It's at a specific size, seems reasonable for dorm room. And she leaves her fan on, 100-watt fan on, right? So she leaves the room on a summer day, hoping that the room will be cooler when she comes back in the evening. But what happens is, assuming that all the doors, windows are tightly closed and there's got any heat transfer to the walls and windows, determine the temperature in the room when she comes back 8 hours later, right? Use specific heat values at room temperature. So what I essentially mean is using your air temperature, was air, of course, is the working fluid here, working medium within this house, that or dormitory. You've got your gas constant at 197, intensity at 20 degrees, basically. Well, yeah, anyway, sorry. Okay, so the first you have to note, because it's a closed room, all the windows are closed, all the window closed, there's no air escaping, so it's essentially a closed volume, right? So in a closed volume process, you have to remember that there is no work being done. The air is not being used for any work, for any mechanical work or any work that matter. So in this case, work will be 0. So then we know that Q is equal to the internal energy, and your internal energy is always equal to your mass times your heat capacity at constant volume times the change in temperature. This is essentially a constant volume process. This is the idea of it. Can be a bit tricky, but yeah. So I think, so of course now we can use PV equals MRT. That should be fairly self-explanatory. So we've got the pressure, it's atmospheric. We've got the volume of the room, so that's how much the volume of air there is, and then you've got your gas constant and you've got your temperature. This 293 is going to be, this is basically 273 plus 20 degrees. I hope you get that. And that's how you can find your mass. Do you get that, Puleng? Can you say yes? Okay, great. So now, if you remember, power, right? So remember there's a fan, and the fan is going. You're not even, the fan is basically, it's a 100-watt fan. And power is equal energy over time. So the fan, in fact, is the reason why the temperature is actually increasing with, well, it's a bit, yeah, it's a bit funny. Yeah, it's, I mean, she's hoping that it'll be cooler, but essentially I think the fan is contributing to the heat in this case. So we basically find out, it's, power is basically the rate of energy. In this case, it's thermal energy we're using. And then we find P times T, and this will give us Q. So the power in this case will be 100 watts times 8 times 3,600. Remember, it's 8 times 3,600 seconds. We're working with base units here, right? So it's seconds. And that is equal to basically MCV T2 minus T1. That's this over here. So your CV at 20 degrees, because it's a function, also a function of temperature, is 718. And then we've got our mass, we've got that, T2 minus 20. You divide out by this. I can show you this quickly on my calculator. Just give me a second. We're nearly done, guys, the lecture. Where are we? Just give me a second. Sharing that. So that's going to be, like I said, it's 100 times 800 times 8 times 3,600 divided by 50, I think it's 57.08, multiplied by 718, and that should give you 70.27. Pulling, do you see that? And essentially over here, what's going to happen is that we're going to basically add 20 because the 20 is on a negative over here. So plus 20, and we should get 90.27 or 90.3. It's a very interesting question. We can always debate that. So Pauline, did you get that? Lando, I'm glad to see you happy. Okay, guys. That's that for the lecture for today. Let me just share the slides again. It's been great. I know it's been I'm glad we actually covered this for your benefit. So please, what I recommend to do, go over this. This is your own homework. Of course, this is just for your own benefit. Go over this here. So it's all the processes combined into a cycle. Make sure you do these to warm up. This is very critical stuff. Depends on Mr. Naidu, Mr. Devet, and Mr. Whiteworth. If they're serious, they can solve these things. We might solve it, but I'd like to move on to the actual applied thermodynamics, and then also populate the table. It'd be very interesting to see if you guys are taking notes. So just the investigation in terms of when we increase these things, what happened to the temperature. I'm just want to see if people are taking note. Or maybe, let's see, we can debate about this. Okay, guys, that's the end of the lecture. I don't know who can identify what this is over here. Has anyone seen this kind of vessel before? Yeah, it's an LNG, right? So liquefied. Can anyone discuss a bit why do you think I'm mentioning this? Liquefied gas, natural gas. Why do you think I'm mentioning this? Kiran, Mpo? Well, it says LNG on the thing, You guys not to talk today?
So I think that thing requires a major refrigeration system to keep to condense the gas into a liquid.
Yes, and why do we do that, Kiran? Fantastic.
Well, it's a safety factor because yeah, that's all I can think of.
Yeah, it's also to reduce the volume as well, so we can carry more gas to ship. So like it reduces it by 600 times essentially. Yeah, you guys can watch the video. Get back to me. It's not exactly it's a thermodynamic thing, but it's a very complicated one because we're changing phase here from gas to liquid. So yeah, and of course it does require a heavy refrigerated system. Yeah. So yeah, I'm just throwing that off there as a fun note. And of course, another application, if you look at this, is a pressure vessel as well. So that gas inside there, which is liquefied, it's under pressure as well. Because when we pressurize it, we can change its state. But anyway, yeah. Okay, guys. Thank you very much. We'll continue this next week, Monday. We won't have lectures Friday. Yeah, I'll see you guys on Wednesday for strength of materials. I will be posting stuff on Blackboard, and I will be seeing you on Thursday for electrotechnology 3. So it's been good. Thank you for attending. Thank you for allowing me to lecture you guys. It's been fun. Okay, cheers.
So you say you're going to load this PowerPoint up now for us, huh?
That is correct.
Thank you.
Okay, cheers, guys.